Hello guys, welcome to another problem solving session with Special Maths Academy. It's me, Obukome Jaifi, and today we'll be looking at a number theory problem from the 15th Middle Europe Mathematical Olympiad 2021 edition held in Croatia. And it says finds all pairs MP of positive integers such that P is prime and 1 plus 2 plus 3 and so on plus n equals 3 into 1 squared plus 2 squared plus so and so plus p squared. Okay, so that's our problem for today. Before we start, I would encourage you to get yourself prepared because this problem is going to take a while. Yeah, it's actually going to use a lot of techniques. Okay, so the first thing we want to do is try to rewrite both sides using what we know. We know this 1 plus 2, the sum of the first n natural numbers is n, and 1 square plus 2 square, sum of the first p squared is p plus 1, 2p plus 1, all over 6. So this means that since equals this, then is 3 times p plus 1, 2p plus 1 all over 6. Okay, then I have that n plus 1 is equals to p plus 1, 2p plus 1. Okay, so we have that. I'm going to wipe out some sections now. I don't want, so I'm cleaning these first parts out. Okay, so we have n plus 1 is equals to p plus 1 over 2p to 2p plus 1. Taking this out. Okay, so far so good. Then the next thing we want to do is p is prime. We problem statement gave this. You can see it here. P is prime. And since p is prime, we know that p plus 1, 2p plus 1 is equals to n plus 1 all over p. And that means, and since this is an integer, not just an integer, a positive integer, it means p divides n plus 1. And then since p is prime, either p divides n or p divides n plus 1. We have either of these holding. So it's, if you're observant, you notice that we'll have two cases to consider now. So this one, p is prime, p divides n, p divides n. This is the first case we want to consider. So in this case, you say let's n equals to p times something. Let me say p times t is also a positive integer. So this initial equation, which is this, the one in pink, let's call this 1. Then we have that pt times pt plus 1 is p. We're just substituting pt for n now into 2p plus 1. Dividing through by p, we have that d pt plus 1 is p plus 1 2p plus 1. Then we can like expand. You expand, we have something like pt square plus t equals 2p square plus 2p plus p plus 1. We have then pt square plus t is equals to 2p square plus 3p plus 1. Okay, so far so good. Then I move everything to this side. I bring all this way. I have 2p square plus p out into 3 minus t square plus 1 minus t is equals to 0. Okay, so far so good. Let me move this way a little. Okay. Now, we know the discriminant. Let's recall something. And given a quadratic, first of all, this is a quadratic equation. Let's actually point this out. This is a quadratic equation. A quadratic in P. And recall that for a given quadratic, ax squared plus bx plus c equals 0. We have something called the discriminant. And this discriminant is d equals b squared minus 4ac. And this is if d is greater than 0. I'm just giving out, this is like a revision. Then x is real. If d is less than 0, x is complex. If d is equals to 0, the equation has 2 equal roots. This is just a condition. As I'm just giving out some things here so you can like follow if you haven't heard of this before. And if d equals m squared, m is some rational number, I guess, or m is a perfect square, then x is rational. This is what this means. Okay, so I'm going to be using that here for this equation. Here, first of all, I'm going to clean this discriminant part out. And just, it's not necessary to our problem, it's just to give you an idea of what we're going to be using here. I'm going to use that now. This equation 2p squared plus p into 3 minus t squared plus 1 minus t equals 0. The discriminant of this equation is 3 minus t squared all squared minus 4 times 2 times 1 minus t. This is okay. I squared, this is 9 minus 6t squared plus t4 minus 8 into 1 minus t. So t is t4 minus 6t squared plus 9 minus 8 plus 8t. T is t4 minus 6t squared plus 8t plus 1. I can rewrite this as t squared minus 3 all squared This is plus 9 minus 3 or plus 8 8. I'm going to show you why I'm doing this soon. Okay, so this is the discriminant of this equation. Why are we using the discriminant? First of all, from the problem, we know p is prime, and that also means that obviously p is a positive integer, and positive integers are actually rational numbers. All positive integers are rational. So since p is prime, since p is an integer, then this quadratic equation here, this one, the one emboxed in pink, has to have its discriminant as a perfect square. Otherwise, the roots will not be real. You can see this from a quadratic formula as a perfect square. You know that this equation, let me just illustrate it so that we're actually clear why it has to be a perfect square. If I use the quadratic formula, I know that p is minus 3 minus t squared plus or minus root 3 minus t squared all squared minus 4 times 2 times 1 minus t all over 2 times 2. So this is the discriminant. So if this, assuming this was irrational, if irrational, or if it's irrational, okay, let me say if it's not a perfect square, first of all, this is equals to d. If d is not a perfect square, then automatically you can see that the p becomes irrational. Which is not possible, which is not supposed to happen. So t has to be a perfect square. So this means t is a perfect square. Okay, so d is a perfect square, good and fine. Then there's also something I want to do on d now, which I want you to see. I'm going to also use another very famous technique here to show you that for some certain values d cannot be a perfect square. Let's see how that works out. d is equals t squared minus 3 all squared plus 8 into t minus 1. And since d is greater than or equals to 1, you know that d plus 8t minus 1 is greater than or equals to 0. So we know this. Then next, I want you to look at let's just play around with some values of t. Let's play around to see. But just for now, we're trying to investigate something. Suppose t equals 1, then d is 1 squared minus 3 all squared plus 8 1 minus 1, which is minus 2 all squared plus 0, which is 4. So this works. Okay, suppose t is 2, 4 is equals to 2 square, in case you can see why. So this is a perfect square. 2 is supposed t is 2. This is something like 2 squared minus 3 all squared plus 8 into 2 minus 1. This is 4 minus 3 all squared plus 1. 2. This is 1 squared plus 1 times 8, sorry. 9. This also works. So let's say suppose t is 3. T is 3 square minus 3 all square plus 8. So 3 minus 1, this is 9 minus 3 all squared plus 8 times 2. This is 36 plus 16 equals 52. And 52, okay, this is not working. So then let's just do for t equals 4 so that you can actually see what I'm telling you. Then t equals 4. This is 4 square minus 3. I know you might not see the point of all this now. You will soon. So that what I want to do might make some sense. Okay, this is equals to 16 minus 3x squared plus 8 times 3. This is 13 squared plus 4. 169 which is 193. Okay, so I think this should be enough to show what I want to illustrate. Okay, we had when d equals, this is d square minus 3l squared plus 8t minus 1. When t equals, let me just write out, when t equals 1, we had t equals 4, which worked. When t equals 2, we had t equals 9 also. But from 3 greater than 3, when t equals 3 and above, yeah, I think we have, let's check, what did we have t as? Okay, when t equals 3, we had t as 52. Okay, t was 52, which is not a perfect square. And now when t equals 4, t was 193. We can continue checking, but we can't check for all the numbers on earth. So at this point, if you might be feeling that we might not be having any solutions from t greater, the case when t is greater than 3 and above. So at this point, it's wise to guess that, okay, let's say conjecture from t greater than or equals to 3, d is not a perfect square. Okay, fine, you've just guessed this. Okay, you said from t greater than or equals to 3, this is not a perfect square. But how are we sure this is true? So we need to prove this. So we prove this now. Observe that this is greater than or equals to. Okay, let me use strictly. Why is this true? So I'm claiming this first one. Let's call this 1. And this is true if and only if d square minus 3 all squared. Okay, I can simply, no need to do much here. You can see why this is true, because um this can like cancel this, and you have this is true if and only if 8t minus 1 is greater than 0, which is true since t is greater than 3, right? This is actually true since t is greater than or equal to 3. So we have this part. So d is greater than t square minus 3 also. Okay, there should be a square here, or square. Then at the same time, let's look at this. Let's look at this. T square. Let's subtract this. Consider this difference. This is t4 minus 4t square plus 4 minus this minus d was t square minus 3 all squared plus 8t minus 1. If you expand this, you have something like t4 minus 4t square plus 4 minus t4 minus 6t square plus 9 plus 8t minus 8. When you do this, when you subtract all this, this should be something like 2t square plus, okay, this should be plus 8. You can check the subtractions by yourself. Minus, okay, subtraction is correct. It's just basic subtraction. Should do this. This is 2t square. Okay, this should be minus 9. Yeah, plus 3 minus 8t. Yeah, is correct. Subtraction is actually correct. It's just an expansion of brackets. You can check this by yourself. Correct. So we have that t square minus 2 all squared minus d is equals to 2t square plus 3 minus 8t, and I can write this as 2t into t minus 4 plus 3, which is greater than, okay, let's say if t is greater than, you can see if t is greater than 4, if t is greater than 4, this is greater than 2 times 4 into 4 minus 4. Okay, if t is greater than or equals to 4 rather, which is greater than, this is 8, greater than or equals to 3, greater than 0, right? This is 8, this is greater than or equals to 3, which is greater than or equals to 0. So we see that t square minus 2 all square minus d greater than 0 or t greater than or equals to 4. So, or rather, this means that d square minus 2 all squared is greater than d or d greater than or equals to 4. And combining this with the fact that d is greater than d square minus 3 all squared or t greater than or equals to 3, I think this is true. Yeah, already proved this. So we have something like d squared minus 3 all squared is less than d is less than t squared minus 2 all squared. Okay, so let's just adjust this bound to make this greater than or equals to 4. So for d greater than or equals to 4. So we see that, how is this useful? Let's adjust it. We just adjusted this for t greater than equals to 4. This will still hold. If t is greater than equals to 4, this still holds. So how is this useful now? Let me paint this in pink. If you look at this, this and this are consecutive integers. Let's look at some numbers. Between 25 and 36, can you find any perfect squares in between 25 and 36? No, because after 25 is 5 square and 36 is 6 square. So these are their consecutive squares. So this is square minus 3 and a square minus 2 squared are consecutive squares. So, and we want d to be a perfect square. Let's say d equals x squared or some x, because d has to be a perfect square. We already agreed that d has to be a perfect square for this to have rational solutions, for p to have rational solutions. We're having something like t squared minus 3 all squared less than x squared less than t squared minus 2 all squared. So something like we have, so this means that this inequality means that there is a perfect square in between two consecutive squares. Which is impossible. This is impossible. It can never happen. That means, this means that for d greater than or equals to 4, d is never a perfect square. Let me use this. So this is what I'm trying to show you by testing all those small cases. So this, we've shown this now. D is never a perfect square. So we just need to know for t less than or equals to 3. Thus, therefore, let me go back to black. Therefore, t is less than or equals to 3. But to know that t less than or equals to 3, we already checked these cases before. You know when t was 1, you can see it by this side. I think it's somewhere around here. Okay, you can see it. We said t is less than or equals to 3. And when t is 1, we know d is 2 squared. When t is 2, we know d is 3 squared. When t is 3, no solutions. D is not a perfect square. So t is either equals to 1 or equals 2. I know that we said that so we can like come back now to our original equation. Let me locate it. Okay. Okay, yes. This equation in pink, this equation here, we can like come back to this and can also use this. We'll be combining this and this. I'm going to like map them both out. So let me just write them here. We know t is either equals to 1 or t is equals to 2. So if we put, so it's either n is equals to p or n is equals to 2p. Let me erase some sections out so we can have space. Erase some sections. Okay. So either n is equals to p or n is equals to 2p. So this is one. And you can, so there are many ways. I think there should be many ways to finish up here, but let's just use this equation in pink. Let's use this. So you can say something like sub case 1 when t equals 1, 2p squared, this is plus p into 3 minus 1 squared plus 1 minus 1. We have something like 2p squared plus 2p equals 0. Then 2p out into p plus 1 equals 0. Then p is either equals to 0 or p is equals to minus 1. Nope. No solutions here. Why? P is prime and minus 1 and 0 are not prime numbers, so we can't work with that. Or we could also have our subcase 2 is somewhere around here. When t is 2, we'll have 2p squared. I'm coming back to this equation in pink now. Plus p into 3 minus 2 squared plus 1 minus 2 equals 0. And I have something like 2p squared minus p minus 1 equals 0. Sections. Something like this. Then this, I think you should be factorizing, so it's something like 2p. Okay, let's see, plus. Factorizing something like p into 2p plus minus 1 into 2p. This p minus 1, 2p plus 1 equals 0, p equals 1. Let me clean this one so we don't have issue. P equals 1 or p equals minus half. Also no solutions. Also no solution. Hence p is prime. Okay, so the sum total of all this is that for the first case we've considered now, for this first case we've considered, there are no solutions at all. So you can say, therefore, for case 1, there are no solutions. So we move on to case 2. The case 2 here, I'll go to another slide, and this slide is already filled. P dividing n plus 1. So let me go to another, add another page. Let me write out the equation again. P plus 1, 2p plus 1. And this is our case 2. P dividing n plus 1, right? So as usual, let's n plus 1 equals p times something. Pn. M is a member of set of positive integers. And I can substitute here, so I have something like this. Then if n, this is pm minus 1 automatically, so I have pm minus 1 times pm equals p plus 1, 2p plus 1, dividing through by p, I have pm minus 1 times m is p plus 1, 2p plus 1, expanding as usual, I have then 2p squared plus 2p. Most of these steps will actually feel familiar to the first one. I hope this gives some solutions. Pm squared minus m. And then we have 2p squared plus 3p plus 1 minus pm squared minus plus m equals 0. We bring it, this is plus p into 3 minus m squared plus 1 plus m equals 0. As usual, then as we did last time, since p is an integer, then discriminant, which is p, which is b squared minus 4ac, is a perfect square. Okay, you can expand this. Is d equals 9 minus 6m, 9 minus 6m squared plus m4 minus 8 minus 8m. If you simplify, this is d equals m4 minus 6m squared plus 1 minus 8m. If I rewrite this is m squared minus 3 all squared plus, okay, sorry about that. Is I just completed the squares. That's what I'm just doing here. Okay. So d is equals to m squared minus 3 all squared minus 8 into 1 plus m. Okay. M is greater than or equals to 1. So as usual, let's see. First of all, we know this. Let's, as what we did last time, when m equals 1, we're just trying to check. You know, d is 1 squared minus 3 all squared minus 8. Okay, m is 1 in this case. This is 4 minus 4 less than 0. We can't even work with this. When m is 2, let's just put no solution. Discriminant cannot be negative. We've already said if discriminant is negative, it has complex roots. We don't want complex roots. We want integer real roots. So we are not considering that. This is 1 4 minus 3 minus 8 times 3, 1 minus 24. No solutions as well. Okay, let me come this way. This is the determinant. Writing it out. Okay. When m equals 3, minus 8, this is 9 minus 3 all squared, is 8 times 3, that is 6. 3 plus 1 is 4, sorry. 4. This works, so we might want to consider this. When m is 4, okay, this is 4 squared minus 3 all squared into 1 plus 4, 10 minus 3, 8 times 5, 169 minus 40, 129. Not a perfect score. So we can't continue checking all the cases like this. So at this point, since we have found one, I don't really know, but let's try doing what we did there, because if you look, this is actually feeling kind of symmetric to what we did earlier. So you might want to consider bringing in a similar approach. Let me clean some stuff I think we don't need, so I can. Let's clean it. So let's write it out again. So we have done for d equals discriminant was m squared, and we have done for d, we've checked m equals 1 2 3 4. So we've checked this for, so let's try doing what we did again. Let's make a conjecture. For 4, okay, we could still do for 5. Let's check for 5, so we just be like we just hit a snag and we just concluded. Let's do for 5. When m equals 5, doesn't really take anything from us. Is 5 squared minus 3 all squared minus 8 into 1 plus 5. This is 25 minus 3 all squared minus 8 times 6. This is 22 all squared minus 48. 484 minus 8. 16, 7, 3, 6. Not a perfect square either. You can check this. So I'm feeling that for m greater than or equals to 4, we might have no solution. Let's just try and see that. Okay, so for m greater than or equals to 4, e is not a perfect square. Let's check. Okay, we know this. Is equally less than. You can prove this by yourself. You can check this. The proof is similar. Just know that if this is true, then it's true if and only if minus 8 and if and only if, which is true, obviously true, since m is greater than or equals to 4. So that takes care of that part. Let me clean this other sections. Obviously it's true since m is then equals to 4. So now comes the second part. Consider, so we have d is less than m squared minus 3r squared. Then I think this also holds. This we're trying to show that it lies between two consecutive integers. You might want to consider this. Okay. This is less than. We have this is d is less than this. And the one before this is, so this should be d less than. The integer before m squared minus 3 is m squared plus 3 minus. I think it should be this. So I'm claiming that d is greater than this. So let's check. Now d is greater than this if and only if okay, let's see. We know d is equals to okay, so d is d minus m squared minus 4 squared will be expanding this, and this is, let me just expand this here. M4, sorry. This is m4 minus 6m squared minus 8m plus 1 minus a expand. This is m4 minus 8m squared plus 16. Subtraction should give you something like 2m squared minus 8m minus 15 is 2m okay, might be a little small. This is, and this is greater than let's see how, when is this positive? If m is greater than 5, this is something like m is greater than 5, we'll have 2m. I want to see when this is positive. Okay, that is not enough. Let's say m greater than 7. And this is This is why in math you have to check many things. Things don't always work out so easily. This is 14 times 3 minus 3 is greater than 0. Okay, so m equals to 7 works. I think m equals 6 also works. Let's check. M equals 6. M greater than or equals to 6 in this part. In all this. If m greater than or equals to 6, and this is for m greater than or equals to 6, this is 2 times 6, 6 minus 4 minus 15, 12 times 2 minus 15, 24 minus 15, 9. So we have that 2m, m minus 4 minus 15 greater than or equals to 9, which is greater than 0 for m greater than or equals to 6. So we have d minus m squared minus 4 squared greater than 0 for m greater than or equals to 6. So I can come here now. So this is greater than m squared minus 4 all squared, or m greater than or equals to 6, and d is less than m squared minus 3 all squared for all m actually. So we have this. So we have this. Combining these two inequalities. So you can see that the major part of the problem was finding this. Okay. We have this. I say for m greater than or equals to 6. So that means for m greater than or equals to 6, therefore we can say, therefore for m greater than or equals to 6, d lies between two perfect squares. And thus there are no solutions. There are no solutions for d there. There are no solutions. Thus there are no solutions because d equals some perfect square. Let's say not possible. A member of the set of positive integers. So this is not possible for m greater than or equals to 6. So we just need to check. So if at all d equals k square or some k, then m is less than 6. So that means m is less than or equals to 5. But we already checked this m less than or equals to 5 cases here. We already checked this. You can see it here that for m less than or equals to 5, you can see them here. For m less than or equals to 5, we have only this. So you can see that for m less than or equals to 5, so for m less than or equals to 5, d equals a square only when m equals 3. And when m equals 3, D is 2 squared, then K something like equals to 2. So let's locate our original equations now. Okay, yeah. I'm cleaning the parts we just did. So let's change this. Let me change this because we actually found that 4 was too weak. That will be n greater equals to 6. So that's why math is actually cool. Sometimes the bound might not work so well. You might need to increase it. So for m greater than equals to 6, we already proved this. So I'm cleaning this out now. We don't need this anymore. We know that m is equals to 3. So m is equals to 3. So you come here and you put 3 here into this equation. Then we have that 2p squared plus p into 3 minus 3. 3 minus 3 squared, sorry, plus 1 plus 3 equals 0. 2p squared plus p into 3 minus 9 plus 4 equals 0. So you have something like 2p squared minus 6p plus 4 equals 0. Dividing 3 by 2, p squared minus 3p plus 2 equals 0. Factorize p minus 2, p minus 1 equals 0. So p is either equals to 2 or p is equals to 1. But p is 2 because since p is prime, p is equals to 2. And we know we said that we also want to come back here. We know we said n, this part in blue. You know n is pm minus 1. So this means that n is 2 and m is 3. N is 6 minus 1. That is 5. So n is 5. So therefore, the solution is the only solution np equals 5, 2. And this actually does work. So I'm going to put it in blue now so you can see it. So with that, we've come to the end of this problem solving session. Yeah, it was a problem. It was actually a good one. Well, you can expect this for most international contests. Yeah, you don't expect them to ask you trivial problems. So yeah, but the main thing, we can just go through the solution again. The main thing was actually showing that for some certain values that of m and whatever m and n for m, and I think we used x for the other variable, that we had the discriminant lying between two perfect squares, and thus it could never be a perfect square. This technique is actually very common in number theory generally, so you might want to practice it out, check out some problems, try solving them, or look at some problems that use this technique. It's actually very common, showing that a number cannot be between two perfect squares by showing that it lies. Showing that a number cannot be perfect square by showing that it lies between two perfect squares. Or you could also come to SMA. We could show you how to do this there, provide you more classes and all. So with that, we've come to the end of the problem solving session. Connect with us as usual on our social media handles: Facebook, WhatsApp, Instagram, and all. You can send us a message or send us an email. Our email address is attached to this post. Then if you're a parent or you're a child watching this and you're interested in math, Olympiad math, contest math, you can take the first step and enroll in our summer camp. Registration is ongoing and closes by 29th of August. So it's bye for now till another problem solving session. My name is Obukomai Jaife, and that's all for this session.